All right, so here we are. We are on slide 12, and we're going to have a picture with 4 different graphs on there. Now, you did this. You did a survivorship curve when you did the graveyard thing, right? And we had said the questions that you were answering with the graveyard assignment was, we had said, when are people likely to die? And with depending on the graveyard and your numbers, you might have seen that, especially in the or before 1950 group, you might have seen that you had a lot of deaths as babies, as infants, and then of course, when's the other time people tend to die? When they're old. But in the middle there, you may have seen, and you would expect to see, you don't tend to die when you are between infant and older, right? And so we have these survivorship curves, and that's one of the examples. You can have mortality as a baby, and then also mortality as an old person, but during the middle part of your lives, you don't die. And so there's a number of organisms out there, like deer, like if you think about white-tailed deer, and you kind of throw out car crash part. So if we say the white-tailed deer in some national park somewhere where they're not being run over by trucks like we have around here, but the white-tailed deer, the baby ones can get killed easily, and then once they get pretty big, it's kind of hard to kill them, right? But then they get old and they die. And that's essentially the same curve as you and I. Now, what about or you could argue that in humans, there's another growth curve that maybe you could argue in modern times. So sort of in, like my mom, when she was born, she was the 4th child. But you know what? She grew up as an only child because the other 3 brothers had all died as infants. Now, once mom, got past that, she lived to be a long, fruitful life. But now, in modern days, we've got really good hospitals and stuff. And so nowadays, we don't have that much infant mortality, I'm happy to say. So we have another curve where basically you're born and you live your life and you die when you're old. So that's a second kind of survivorship curve. And that is what you see with like elephants. I mean, who's going to attack a baby? I mean, a baby elephant is probably, well, I don't know how much they weigh, but 300-400 pounds. So they're already born, big enough to be hard to kill. All right. What about songbirds? When do you think they would tend to die? What about when they're a little tiny baby in the nest? Yeah, stuff kills them. Yeah. And then once they start flying, yeah, they get killed. And then as they get bigger and they're more mature and they're flying around, yeah, they're still killed. And then when they're old birds, they're still killed. So what I'm trying to say is there are some species like songbirds that it doesn't matter how old they are, they could die at any minute. And so they have a very straight curve. So let me show you these. The very first curve I was talking about is this one here. A lot of death as a baby, no death, and then old. Then we had said humans and elephants, not much death until you get old. Then here we have birds. So that's the third of 4 growth curves. Now, what about oak trees? So if you think of an oak tree, and what is a baby when you talk about a tree? It'd be an acorn that sprouted, right? So you might have, or I'm going to say maple trees. You know those seeds, they kind of spin around and they fly everywhere. And if you have gutters, you'll look out to your gutters along about June, and you'll see all these little trees coming out of it. And what do? You get the ladder, you go over there, you scoop it out, and you kill all of those little trees, right? You can't have a maple tree growing in your gutter. So if you are a tree, almost all of the babies die, almost all of those seeds die, except for a few. And those few, once they take hold and they get pretty good size, why, they're going to live for 300 years. Unless somebody, some hoodlum comes along and cuts them down. But for the most part, they're going to live. So they have super high mortality as a baby, those little tiny seedlings. But once they reach a certain size, they're going to live for 300 years and die as an old tree. So the final curve is you have this crash in the population, huge mortality in the trees, and then any that survive live for a really long time. So those are the 4 different survivorship curves that we have for for different species. Okay, so we have some words. We have some words that we hear about all the time, and I've even been using some of them. When we talk about abundances, what do we mean? We mean the number of individuals within a species. So you say, what is the abundance of white-tailed deer? And it'd be a lot. There's a whole lot of them out there. But what about the diversity? When we talk about diversity, and we hear this term all the time, biodiversity, right? What about biodiversity? What are we saying? We're not saying we got a whole lot of white-tailed deer. No. We're saying you got your white-tailed deer, you got your red foxes, you got your possums, you got your field mice, you've got your raccoons, et cetera, et cetera, et cetera. This is biodiversity, having a lot of different species. Okay, so where do we see the greatest abundances and biodiversities? Abundances are meaning numbers of individuals in a single species, and diversity meaning the number of different species in an ecosystem. And it ends up, there's a rule for that. At the equator, you get real high diversity, lots and lots of different species, but any given one species doesn't have that many individuals. And because remember I said with the stabilizing selection, I said that you have this habitat partitioning resource, so that so you have lots of different species, but each one is only utilizing a small part of the resource. Okay, so at the equator, we have high biodiversity, but low abundances. Now, what about at the poles? At the North Pole and at the South Pole, or as you approach them? What can you tell me about life there? Is it easier or harder to live there than at the equator? The answer is, of course, it's much harder. Much harder to survive in that kind of a climate. So, the species that can survive up towards the North and the South Pole, they don't have as much competition. And so you have lower diversity, but much higher abundances. And that's as a general rule. That's what you see. Okay, we're moving right along. So when we talk about communities and community ecology, I'm putting in a plug for some of my people that trained me. This handsome young man is called Dr. Donald E. Harper, and he's a retired guy now. He's even older than me. But he was one of my professors, and he was what you call a community ecologist. And so he studied the groups of organisms living in different locations. And so when we talk about when you talk about what are the kinds of things that a community ecologist will study, it'd be where are individuals, how are they spaced out throughout the community, how are the various communities positioned on the surface of the earth, geographic locations. Do the communities have uniformity from interior to outside, et cetera, et cetera? So these were the kinds of things that a community ecologist will study. Now, what are they good for? What are they good for? Well, what about those oil spills I was talking about? So I mentioned at the beginning of the semester that I had taken part in some what do we call it? Environmental impact studies in the areas where they're drilling for oil in the Gulf of Mexico. And it was with this guy, Don Harper. And so as one of his students, I was doing a lot of oceanographic work, and we were looking at what are the communities that are out there where they're drilling oil. And why were we doing that? Well, it was just in case there happened to be an oil spill, which there was. And then if there is an oil spill, you say, well, what damage was done? Well, how do you know? Oh, you can compare the community after the oil spill to the community before the oil spill, the stuff that we did. And so that's what we were doing. That's what we were doing, and that's what Don Harper did throughout his whole career. All right, so when we talk about one of the points that I mentioned on that last slide was the distribution of individuals. I am on slide 15 right now, and I'm going to finish this slide, and we'll stop and do one more recording. So we have the distribution of individuals on land. It can be one of three different forms. It can be random. That means they're just wherever they happen to land, right? So if you're talking about sea creatures that are plankton and they just sort of happen to, as they mature, they become an adult, and it's wherever they are is where they find themselves, that would be random. If you have grumpy individuals, if they're so grumpy that they keep people away or keep other individuals away from them, you end up with a uniform distribution. And so if you think of some of these islands where they show birds nesting, and when you look at it, and I have some pictures that you'll see on the slides, you'll see they're all equally spaced away from each other, the nest, one right next to the other, but they're all, and the distance they're apart is how far their neighbor can reach over and peck. And so they're uniformly distributed. Now, what's the other alternative? Maybe they don't dislike each other. Maybe they can't stand being alone. Do you know anything about cows? Cows can't stand being by themselves. Same way with deer. If you ever see one deer cross the road in front of you and you look to where it came from and you see others, you better stop, because those others are going to get scared and they're going to at the last second try and run in front of you, and they're going to end up on your hood. This is a clustered or clumped type distribution. So we can have random, uniform, or clustered and clumped. Clustered and clumped, they're attracted to each other. Uniform, they're repelled by each other. And random, well, that's just random. All right, I'm going to stop here. We'll be right back with one more.